Hello everyone, thank you for joining us here for our virtual design day. Our team number is 19028. We are the Slide Randomizer team. Our sponsors are from Roche Tissue Diagnostics and our mentor is Steve Larimore. This is a photo of our team. In the top row we have Jake and Kazane who are studying mechanical engineering and Brittany who has her Associates of Applied Science in Computer Aided Design. In the bottom row, we have Sierra, who is studying electrical and computer engineering, Elizabeth, who is studying engineering management, and Sierra, who is studying biomedical engineering. This is an image of our Design Day poster. We will be going more in depth for each of the sections shown on this poster throughout this presentation. We will first begin by explaining the problem description, current testing methods, and our goals. We will then explain our methods and the makeup of our system, followed by our detailed designs, the device's operation, and our requirements verifications. And finally, we will talk about our conclusions, our path going forward, including a second-generation design.
Firstly, we would like to provide a short background about some of the motivations of this project. Roche is a company that helps diagnose, treat, and perform research on various types of cancers. A pathologist's role in the company is to evaluate stained human tissue on glass microscope slides, differentiate different types of cells under the microscope, and diagnose and perform research on the causes and effects of different diseases. However, in order for a pathologist to reach their certification, they must perform a test that demonstrates their ability to correctly evaluate the stained glass microscope slides. The current test involves several steps to set up and execute for both the trainer and the pathologist taking the test.
This figure explains how the current test is set up and performed. The trainer must manually arrange and randomize 40 to 60 cases of slides, with each case consisting of 3 glass slides. All of the slides are then sent to the pathologist to perform their examination. When finished, the pathologist's answers and all of the slides are then sent back to the trainer to decide if they pass or fail. If the pathologist fails, the process is then repeated again.
Our task is to improve the current pathological testing process by creating a lightweight, transportable testing device that pathologists can use to analyze stained glass microscope slides and record their answers. This device will eliminate the tedious manual setup and execution of the test. Some of the major components were to include that the device could store 40 to 60 cases, it was lightweight and transportable, it can generate or accept a randomized order, it can output each case in the correct order, it can store user input and test answers, and have the ability to extract the test answers for evaluation.
To come up with the best possible solution, we determined what shape to build the device in order to meet its transportation requirements. We performed some preliminary research and came up with 3 initial designs: the carousel, the LED tray, and the 3-arm claw. In our trade study, we largely focused on the cost, size, weight, reliability, simplicity, and slide storage efficiency. After further analysis, it was decided that the carousel and the claw were just not practical in terms of size, weight, and complexity. The LED tray was simple yet met all of the requirements. To build the structure frame of the device, we decided to 3D print the entire structure using ABS plastic. We then had to explore how we would attach the hardware to the frame securely. After performing some additional research, we decided that we could use heat set inserts to assemble the hardware. To ensure that these would work, we performed a series of torque tests with some sample ABS pieces. Ultimately, we decided that the heat set inserts would work perfectly with the device. Finally, we wanted to make sure that the slides did not break during transportation, so we created custom foam inserts made out of anti-static polyethylene foam to protect the slide.
For the electrical and software components, we chose to use a Raspberry Pi 3B Plus as the brain of the device. Attached to the Pi would include all the device's necessary components, including each of the individual LEDs. In order to attach all the LEDs, we needed to use 2 GPIO expander bonnets to increase the number of usable pins on the Raspberry Pi. The video below shows some testing performed to ensure the LEDs would illuminate. To program the graphical user interface, we used Python's Tkinter package and Python 3 language. Shown here is a system block diagram of the entire device. As you can see, the main processing unit of the device is a Raspberry Pi. The CPU is then connected to a touchscreen display, keyboard, extra USB port, barcode scanner, and finally, the GPIO expander bonnets to communicate with the individual LEDs. The device can be powered on through an on-off switch located on the power cord connected to the wall. Here we have the overall design of the Slide Randomizer device. As you can see, the device is just under 2 feet long, 1 foot wide, 6 inches tall, and just over 20 pounds. The size and weight of the device meets the TSA regulations for carry-on luggage. Enclosed with the draw latch lid, the main faceplate of the device consists of a touchscreen display, keyboard, barcode scanner, USB port, LEDs, glass slide slots, and a slide cushion. Shown on the right-hand side are some of the device's main graphical user interface pages. During the test setup portion, the trainer can scan each slide barcode, and the software will notify the user which slot to place the glass slide into by signaling an LED. The trainer can then choose if they would like to import a randomization order or generate a new one. At this point, the test has been set up, and the pathologist can now perform the test. The main testing page is shown in the bottom right corner. Here you can see that the pathologist is prompted to scan the slides of the illuminated case. The pathologist then has the option to select multiple answers, input comments, save their answers, or move on to the next case. Once finished with the test, the trainer can then go back into the setup pages and choose where they would like to export the testing data. Alright, so when we open up the device, this is the first thing that we see. We have a little icon here where we can open up our test. So we'll go ahead and open that up. And it takes us into our home screen where we can take the test or set up the test. We'll go ahead and do a sample setup and enter in our PIN. Right now it's 1234, but we could change that later on if we'd like. We'll go ahead and hit test setup and select a setup file. We have a sample setup file to read, and then we'll open that up. We can then go ahead and set up our test by scanning a slide. So we'll go ahead and scan a slide here, and then we'll read the barcode, and it will tell us where to place that slide so we can illuminate that slot and slide it in there. Once our test is all set up, we can go in and choose a randomization order. So we'll generate a randomization order here, or we could just use the one from the setup file. Then we'll go back to home, say we want to take the test, and then you enter in your name here. So we'll just type in name, and then we'll save, and then we'll begin our test. It takes us into our testing page where we can start the test. And as you can see, we have lots of questions here, answers, little toggle buttons, so we can go in here, choose our answers, type in numbers here, and then save our answers. Then once we save our answers, we can go on to the next case. And as you can see, the cases will change as we change through the different cases. And once we're all finished, we can end our test and say, yes, I am finished, go back to home, and then we are all done with the test. If we want to extract the data file, we can go back into the setup here, type in our PIN, data file randomization, and choose where we'd like to export our data. Shown here are some photos of the progress we made during the construction of the device. As you can see, we went from a pieced together 3D printed frame to a full frame assembly.
Shown here are all the acceptance tests that were conducted. The automation and data file acceptance tests were performed at the computer subsystem level on April 11th and have both passed. The illumination accuracy, time, case delivery, and repetition acceptance tests were all performed at the full system level on April 11th and all have passed as well. The last test that was performed was the vibration test, which was performed on April 17th and passed as well. These acceptance tests were conducted to show that the key requirements were met and the main objectives for the device were complete.
This is a list of deliverables to our sponsor. We'll be delivering all of these items both virtually through a shared drive and physically to Frank Ventura by May 4th, 2020. This project has been a learning experience for all of our team members. One of the largest surprises for the team was finding out how long it took to 3D print the frame of the device, which was nearly 1,000 hours. We were able to learn from this and implement new ideas into our next generation designs. The team was also faced with challenges, especially during this unpredictable time. We were able to obtain all necessary components for the device and perform equipment tests prior to the campus being shut down. We also overcame our largest risk of minimal software knowledge and graphical interface development. One of our team members was able to learn Python 3 programming language outside of school to create a fully functional graphical user interface. One of the key lessons our team learned was that there are more cost-effective and efficient ways to generate the structural frame other than 3D printing. Our team also learned that prototyping early was key to our success.
In conclusion, all the system requirements have been met and all the acceptance tests have passed without any issues. The design serves as a proof of concept prototype as well as a temporary full use device due to the impacts of COVID-19. Our team was able to prevail even when the circumstances changed drastically. We learned much from creating this device and are using information to create a next generation design, shown to the right. The next generation design will include replacing the 3D frame with a commercial case, and the faceplate will be adjusted accordingly. The benefits of these changes reduce the time and money spent on the frame, as well as make the device more widely available. Another feature we added for the next generation design will be making it more compact and include a long-lasting battery power for easier transportability. Finally, we would like to thank our sponsors Frank Ventura, Joe Herndon, and Vi Wen from Roche Tissue Diagnostics. We would also like to thank our mentor Steve Larimore for all of his undoubted efforts. Lastly, we'd like to thank those of you who are listening in and for taking time to view our presentation.